Okay, so we went through a very long presentation in the lecture notes for this chapter. Let's look at the work problems, which are also kind of long. And in fact, I may actually, I'll try to go through all of them if I can make myself do it, but there may be one or two that I'll just let you do on your own, but we'll see. So I want to go ahead and quickly give the credits, and I'm going to have to kind of go fast through these as I did with the lecture notes. So Brown and LeMay and Zumdahl's chemistry and McMurray and Fay's chemistry are the sources that I used for some of the problems. And each was probably used a little bit, and then also Mr. Mack's AP chemistry site, which is a very useful site. Let's go on, and also the answers are provided by myself. Next slide. And I'm going to go ahead and just click through these first few slides. All right, first one here. I think maybe this one I should let you guys do at least part of this on your own because it's so trivial. So let me get my marker working and we'll just do the first one together. This is going to be your acid for part A, and this is going to be your base. And then what's left over of your acid after it donates your proton is going to be the conjugate base of the acid. And then what you get when you add a proton to your base is going to be the conjugate acid of that base. So this is the acid, this is the base, and then this is going to be the conjugate acid, and this is going to be the conjugate base. And it's a little confusing, okay? So you'll want to make sure you understand this as quickly as you possibly can so that you have it straight in your mind. So I'll let you guys do these two. Most of the other ones that we're going to do, I'll probably go ahead and do them, at least unless I start to run out of time. Next slide. And then here are your answers. Next slide. Find the OH minus concentration of each of these. So what you have to do here is, if you know the H plus concentration, as we said in the lecture notes, and this is one chapter where you probably should go back if you haven't already done it and watch the lecture notes, even though it's 2 hours, because if you don't, you may be able to figure this stuff out anyway, but and some of you probably can, but it would probably be better if you have the time at all, just go back and watch the lecture notes. But anyway, I'll leave it up to you. But as we said, what you have to do for this kind of a problem is remember the concentration of the H plus or H3O plus times the concentration of OH minus always equals the same number if you have pure water. And as I also mentioned, tap water is not pure water, so it won't work for tap water. So you should be aware of that. But so if you multiply the OH minus times the H plus concentrations, you get 1 times 10 to the minus 14th, which means that for each of these, what you can do is you can take 1 times 10 to the minus 14th and divide it by each of these four numbers in turn and get the OH minus concentration. So let's actually just go on to the next slide, and I'll just show you what I got when I did that. Excuse me. So for A, I took 1 times 10 to the minus 14th, and I divided it by this number, 1e minus 7. Well, I could just look at that and see it's going to be 1 times 10 to the minus 7th. And this is what you have in pure water. You have a concentration of both H plus and OH minus of the same 1 times 10 to the minus 7th. For B, 1 times 10 to the minus 14 divided by that number right there gave me 12. You'll want to do this on your own if you have time. Just make sure you can do it on your calculator, because of, make sure the exponents and everything, you know how to do them. For C, it's actually just the reverse of B, but you would divide 1 times 10 to the minus 14th by 12, and you would get 8.33 times 10 to the minus 16th. And for D, 1 times 10 to the minus 14th divided by 5.4 times 10 to the minus 5th is going to give you 1.9 times 10 to the minus 10th. Next slide. What are the major species? Let's do that first. So the major species for these. So first of all, look at these two acids. It's perchloric acid and nitric acid. Are they strong or weak? And we can't answer the question unless we know that. So are these two acids in our list of 7 acids that were strong acids? The answer is yes. So what that means is if we put either one of these in water, they're going to break up completely, or we're going to assume that they break up completely into H plus, which we're going to designate as H3O plus, in the case of A, it would be ClO4 minus, and for B, it would be NO3 minus. And then, of course, you'll always have water. And then to do the pH, since these are both strong acids, you're going to get the same value. So all you have to do, since they're strong acids, we assume that the concentration of the H3O plus for both of these is going to be 0.25. So all you have to do, and see if you can remember how we did these before I tell you. How did we get the pH for strong acids? We just took minus the base 10 log of the concentration of H plus. But you say, but this isn't the concentration of H plus. Yeah, I know. It's the concentration of HClO4 for A and HNO3 for B. But remember, we assume that they break up completely, so we assume that the concentration of H plus will be the same as the original concentration of the acid, which is 0.25. So we take minus the base 10 log, the log log of 0.25 for both of these, and whatever we get when we do that, we have the pH. Let's go to the next slide. And we should get the same answer for both, and we do. And it is 0.602. So again, I recommend that you go ahead and do these on your calculator and use the same calculator you're going to use on the exams. I mean, this probably sounds obvious, but it just, I mean, even in 1412, it happens that people come in and we start the test. I mean, I'm talking about doing it in a classroom, but it would even be worse if we're under a lockdown browser and this happens. But and actually, I'm not even sure how that works. But anyway, if you're going to have to use a calculator on the screen, if you're doing it for a lockdown browser, I actually don't know how it works, so I need to check that out. You'll want to make sure you understand how to use that. And usually the ones on screens are crappy, especially for our purposes. It's usually really hard, which is one reason I've kind of like resisted using those things. Anyway, but just be sure that whatever calculator you're going to be using on the test, which hopefully we'll be able to tell you that before the test well in advance, that you know how to do these kinds of problems. Anyway, I've said enough about that. So just take minus the base 10 log of 0.25 and you get 0.602. Let's go on. All right, so I just put this in for you if you didn't already know. Here is the list of strong acids and strong bases, which I'm not going to go back through them. But if you don't remember them, you can pause this and look at these. And let's go on to the next slide. Find the pH of each of the following solutions. And I can do A in my head, and I can also do C in my head, and I can't do B, but I can give you an estimate. So let's do A first. And I'll actually try to write this out. So what is 0.1? 0.1 can be rewritten as what? 10 to what power? 10 to the minus 1, right? So what's the log of 10 to the minus 1? It's minus 1. And what is minus 1? Plus 1. So what's the pH here? It's just plus 1. However, we have to write it as plus 1, or you don't have to put the plus sign in. But we have two sig figs in the concentration, right? Over here, the 1 and the 0 on the right is significant, so we need 2 decimals, right? Remember this from the lecture notes. For C, we can just look at this and we can see that this is a strong acid, but it's present in a lower quantity here than the water itself has. The water has more H plus than the HCl does, because the water has 10 to the minus 7th. So we use the waters instead. And so that's one of the things I was talking about at the end towards of the lecture notes, was that it's very rare that you would use the autodissociation of water, but part C here would be one example of that. You have more H plus just floating around naturally in the water from the autodissociation of water than you have, by far, than you have of this HCl you put in. So if the concentration of the H plus in water is 10 to the minus 7th, you take minus the minus 7 and you get plus 7, and you want 2 decimals, which I'm not going to write this out. Sorry about that mark there, but it will be 7.00. Now let's look at B. Remember I told you at the very beginning of the lecture notes for this chapter, whenever you have more than 1 molar of a strong acid or base, you end up either lower than 0 for the acids or more than 14 for the base. And that's what we have here. So I don't remember the exact number, but what we're going to actually wind up with here should be a negative pH. It should be less than 0. So if you think about it, if it were 10 to the 0 is 1, so if it's 1 molar, you would have a pH of 0. So if it's anything more than that, then it's going to be actually a negative number. So, and I can't remember what it is, so let's actually flip over and look at the answers now. So it is going to be this one right here. So the pH of that 5 molar HCl will actually be minus 0.7. And then the others are just as I said. Let's go to the next slide. What are the major species present in 0.25 molar solutions of each of the following? I only chose 2, and find the pHs. In this case, the pHs won't be the same. Why? So look at this for a moment while I sit down. Okay, so why will we not get the same answer for A and B? Well, because these are not strong acids, right? They're both weak acids. So what do we have to do in order to solve for a weak acid's pH? Well, we can't just take minus the log of the concentration, right? We have to do what? We have to make an ice table. And what are we going to use for the concentration of the original acid? For both of these, we're going to use 0.25. So I made up 2 ice tables, one for A and one for B. We have the Ka values that were given. They're not in the problem statement, so I'll put them there for you. But they would have to be given to you in order to be able to solve these. So let's go ahead and move on. Well, before we do, let's just kind of let's just try to set up the first one. So what are we going to be reacting HNO2 with? In order to get a Ka expression, we have to get a Ka expression to use the Ka, right? So that gives it away. What do we always have to react something with to get a Ka expression? Water. So we're going to have HNO2 plus water. And what's that going to give us? The H plus will come off the HNO2 and make H3O plus and leave us with NO2 minus, right? And it'll be the same thing for B. All right, so we'll have that as one of our equilibria. That will be the Ka equilibrium, and then we'll also have the auto dissociation of water. But I guarantee you in every problem that the constant, the Ka value for your weak acid will be larger than 10 to the minus 14th. So just assume that you're going to write across the top of your ice table for part A, HNO2 plus H2O gives NO2 minus plus H3O plus. And then assume that your product's concentrations are 0 to start. What are you going to assume for your concentration for your HNO2? Well, what was given to you, which was 0.25 molar. And it's going to be 1 to 1 to 1, so just minus x plus x plus x. You're going to wind up with x and x, and so it'll be x times x divided by 0.25 equals Ka. So let's go ahead and go to the next slide. So you end up down here, and you can look at the rest of this if you want to pause this. We're going to assume that that x is negligible. And I don't see anything here to indicate otherwise. So we wind up with that the Ka is x squared over 0.25 and solve for x. So you're going to have to take a square root in there somewhere. And when you do this, you get that x is 0.01. So that means that that is 0.01 and that is 0.01. But most of the time, unless they ask you to find the concentrations of all species, which they don't here, then the only thing you're going to care about if they're asking for the pH is the concentration of this, or if it's a weak base problem, you want the concentration of the OH minus. So the concentration, and we can just look at this, right? So the concentration of the H3O plus is this, which is something we can rewrite as 10 to the minus what? And think about that for a minute, because it's important that you get used to doing this mentally. What is that in terms of 10 raised to some power? Well, it's 10 to the minus 2, right? So what's the exponent in 10 to the minus 2? It's minus 2, so that's the log. So that's the base 10 log. So take minus the minus 2 and you get plus 2, and that's your answer. The reason that I have these 3 zeros here is because in the problem statement, they have 3 sig figs where that 0 all the way to the right is significant because somebody stuck it in there on purpose to let us know that it is significant. Next slide. And here's the answer for B, which I'll let you look at on your own because it's exactly the same as what we just did. It's just that the numbers are going to be, the number here for your constant is going to be different. Otherwise, it's the same thing. So let's go on to the next slide. All right, calculate the concentration. And now this one, they want all the species. That means we just have to do a little bit more work, but it isn't a big deal. So we'll have to say whatever we get for X will be not only the concentration of H3O plus, but also, in this case, it would be the concentration of F minus. And then to get the original, or to get the equilibrium concentration of HF, we'll have to take the 0.02, and wow, that's a really small one. So this one we may have to use the, what's it called? The quadratic equation. Anyway, so we would, when we find X, we'll have to subtract it from 0.02. So otherwise, we'll set this up the same way as the ones before. So let's just go ahead and take a look at the answer. Next slide. And let me see, yeah, this one we do have to use the quadratic equation. And the main reason is because that initial concentration is so tiny. Remember, that's what you're going to be dividing into. So whenever you see something like that, I mean, I probably wouldn't give that on a test. Or even if I did, I'd just tell you forget about using the quadratic equation. Because that's not the purpose of our chemistry class. You should have learned that in high school. So anyway, but just so you'll be aware of it, whenever you have a really tiny initial concentration here, then that's what you're dividing into. So that's going to make it very likely that you're going to get a large error. Anyway, having said that, we start off the same way we always do. Everything here is set up exactly the same way as we did in the previous problems. There were like 3 other problems just like this. The only difference is when we solve for X, then we divide that by 0.02 to get the error. We get a huge error, which is obviously more than 5%. So I said, okay, well, for this one, let's go ahead and use the quadratic equation. So in other words, we go back and we start over again and we leave that X in there and set it up. And when we do that, and when we rearrange it to get it like ax squared plus bx plus c equals 0, we get that a is 1 here, b is 7.2 e minus 4, c is minus 1.44 e minus 5, and then plug that into either a web page that does this automatically or your calculator and solve for x, and you'll get 2 roots, and you want to figure out which roots you need to keep. And in this case, it was the 0.00345, which if you look, when we did it the first time by assuming x was negligible, we got 0.0038. So, I mean, that's slightly different, but I mean, it's not like the end of the world different. And also notice that the original error here was 19%. What's this error? This is still 17%. So look, I mean, it's better, but it's still not anywhere near perfect, right? That's the best we can get, is 17% error. So anyway, when we redo it, we're going to use the value we got from that. So x is going to be 0.00345, and that's going to be here and here, and then we'll subtract 0.00345 from 0.02 to get what goes right there. Remember, what we care about is the equilibrium concentration for HF, not its initial concentration. Then we'll multiply this number here by itself, this number here, because it's going to be x squared over 0.02 minus x. So multiply this number by itself and then divide it by whatever you get when you subtract, which is going to be 0.01655. And whatever that is you get, there is going to be your Ka value. Okay, and so anyway, and then so reading back, what it actually asked for here was the concentration of all species. So whatever you got for X will be the concentration of your H3O plus and your F minus. And then whatever you get when you subtract X from 0.02 here will be the concentration of HF. And then the pH, to get the pH, you just take your X and take minus the base 10 log of that, and that will give you your pH, which is, I'm trying to figure out where I did that, and I'm not seeing it. Here it is. Okay, it was kind of out of place. So minus the base 10 log of 0.00345 is 2.46. So that is going to be your pH. Notice here I also did it for OH minus just because that's present. So technically, to do all species present, you'd have to do OH minus 2, but you don't really have to do that. So just, I'm going to put a parenthesis around that. So for my test, you don't have to put that part in. So just, I mean, it's enough if you figure out what that is at equilibrium, and what that is at equilibrium, and then also find the pH. Next slide. For propanoic acid, determine the concentration again of all species present, the pH, and the percent dissociation, which this last part's usually very trivial. So let's go ahead and look at that. I'm going to just go ahead and go to the answer here. So we're starting off with 0.1 molar, which I'm going to put here. Otherwise, the other things we're going to assume are 0. Again, we have 1 to 1 to 1. So minus x on the left, plus x on the right. Assume that the x is negligible, and in this case, it turns out to be okay. And that's even though this is, again, this is a very small number too. However, the reason it's okay is because the Ka value is really small. So when you divide what you're going to get, your x is also going to be really small because that Ka is so small. So anyway, to get the x, we do x squared divided by 0.1, and that's going to equal the Ka, which is 1.3 times 10 to the minus fifth, and I'm reading that from the problem statement up here. X squared divided by 0.1 is 1.3 times 10 to the minus fifth, and that's also written down here somewhere. Here. And then just solve for x. Again, you'll have to take a square root in there somewhere, and you get that it's 0.00114, but then when you divide that little tiny number by this number, even though this number is also small, but when you divide this really incredibly tiny number by 0.1, you're still okay. I didn't write down what it is, but I'm guessing it's about 1%, so it's okay. So what does that mean? It means we don't have to do the quadratic equation. That's all it means. So anyway, the concentration of H3O plus is going to be what we got when we got X. It's just going to be 0.00114 molar. Same thing here. That's the propanoid, and then the propanoic acid will be whatever number you get when you subtract 0.1 minus 0.00114. And then you could also do the OH minus if you want to, but you don't have to. To get it, all you have to do is divide 1 times 10 to the minus 14th by that number right there. And then it also wanted us to do the percent dissociation. So just whatever you got here for X, which was 0.00114, divide that by 0.1. And that's also exactly the same way that you do your error. And it did turn out to be about 1%, as I said. So it's 1.1%. And then the only thing that we did not do was the pH. And to do that, just take minus the log of X, which was 0.00114. And I'm looking to see where I did that. And here it is. Okay, so minus the log of 0.00114 is 2.943. Next slide. So we can take a little bit of a break here and do some multiple choices. So 1, the conjugate base of HSO4. What would you have left here if you took 1 proton off of HSO4? You would have B, SO4 2 minus. The molar concentration, number 2, of hydronium, that's H3O plus, hydronium ion, in pure water is 1 times 10 to the minus 7th. And what is the pH of an, so number 3, what is the pH of an aqueous solution in which OH minus is 0.0025? Again, there are 2 ways you can do most of these problems. And I don't remember which way I did it on the answer. One way you could do it would be to go ahead and just find the pOH using the 0.0025. So what you would do is just type in 0.0025 into your calculator and take the log of it, and then take the negative of that. That would give you the pOH, right? And then subtract whatever you get from 14, and that will give you the pH. Now, there's another way you could do it where you could divide 1 times 10 to the minus 14th by 0.0025, and that will give you the concentration of the H3O plus, and then take minus the log of that. You should get the same answer regardless of which way you do it, and I think that is the answer right there. So let's go to the next slide, and let's let you pause that if you want, otherwise I'm going to go on. Next slide. Number 4, which of the following cannot act as a Lewis base? So A base is a proton acceptor, and I don't usually I try not to write, but in this case I'll write PA, which means proton acceptor, or it can be an electron donor if you're looking at it in the Lewis sense, which is what we're talking about here. So a base would be something that donates electrons. So it would have to be something that has an extra electron pair. So here the O has 2 lone pairs, so it would work. The N has 1, it would work. The Cl minus has 4, so it would work. The F here also has lone pairs, and the N here has lone pairs. But the thing is that these Fs here are on this boron, and this boron is electron deficient. The boron is number 4 in the chart, so it has 4 valence electrons, and it tends to only end up usually with 6. Oh, let's see, is that right? It had I'm sorry, it has 3 valence electrons. So it can tend to make 3 bonds, which gives it 6 electrons in its valence shell, but it wants 8, and so because of that, it cannot act as a Lewis base. And the reason is because it actually needs more, so it would act as a Lewis acid. In other words, what I'm saying is that boron doesn't have enough electrons around it. It only has 6 in that particular case, because each of those fluorides will make a bond with the boron, and so the boron will wind up with 3 bonds around it, which have 2 electrons each, for a total of 6, but it wants 8. So actually the boron doesn't have enough electrons, so it's not going to be donating any of the ones it has. It needs more. So actually the boron will usually, maybe always, act as a Lewis acid, not a Lewis base. And in fact, usually when they ask a question like this, if they're asking which of the following can act as a Lewis acid, if there's an answer choice in there that has a boron in it, that's always the right answer. Okay, now this is what we talked about, number 5, at the very end of the lecture notes, where I told you that whenever you have something that's a nonmetal that makes an oxide, it will be covalent. And so when you drop it in water and it becomes something like H2SO4 or HNO3, then that covalent bond between that oxygen and the thing that it bonded to, like the S or the N, will not break. So what will come off will be the H. So metal oxides are typically, well, let me finish what I was going to say. So we were talking about nonmetals there. So these are going to typically be acidic, and metal oxides, like calcium oxide, when you put them in water, will make things like calcium hydroxide, where anyway, the main point is that the bond between the calcium and the oxygen is ionic, and it will break when you put it in water. But when it breaks, if you put it in water, the O will accumulate an H and it'll become OH minus. Actually, when you put it in water, it's going to form calcium hydroxide, which is CaOH2, and then what will happen is those 2 OHs will come off when you put it in water and dissociate, and so you'll have OH minus, which is basic. So these are going to tend to be basic, and the nonmetals are going to tend to be acidic, so our answer is going to be C. And if you can't remember this any other way, just memorize it, because it's almost for sure it's going to be on both your in-term and also in your final exam. So here are your answers. Let's go to the next slide. We're going to have to do some more of the hard stuff after these multiple choices, so we don't want to relax too much. Which of the following ions will act as a weak base in water? Now, this is a little confusing, so let me just explain the trick here. What this means is that if you have the conjugate base of a strong acid, it will not act as a weak base in water. And you probably are confused by this, so let me say it again. If you put a strong acid in water and it breaks up, its conjugate base will not be as strong as the water itself, because it was originally a strong acid. That means that its conjugate base will be weaker than water, which means that it will not act as a weak base in water. Why? Because there's more water, and the water is a better base. So the only way you could get something to act as a weak base in water would be if it were something that is a stronger base than water. And if you remember from the lecture slides, we said that would be when you have a weak acid. when you have a weak acid, its conjugate base will be stronger than water. So what we need to do is look at these four choices and find one that's coming from a weak acid. So why don't we start at the bottom and work up, and let's assume it's not going to be E. Is OH minus a weak base or coming from a weak acid? No. What about NO? That's actually a strong base, so that won't. Now, the reason that D is wrong is for a different reason than the next two, and that's because OH minus acts as a strong base in water, not a weak base. For these two choices here, Cl minus is coming from HCl and NO3 minus is coming from HNO3. Those are both strong acids. Their conjugate bases, therefore, will be weaker as far as their base properties than water itself, so no, they won't work. So for different reasons, these two won't work either. So what about A? Well, what acid would you get if you put an H on ClO? You'd get HClO, which happens to be perchloric acid. I'm sorry, that's wrong. It's hypochlorous acid. Hypochlorous acid, excuse me. So that turns out to be a weak acid. So its conjugate base will be a stronger base than water, so the answer is going to be A. So that was a lot of talking to explain that, but it's important that you understand that. Number 7, an aqueous solution of blank will produce a basic solution. And so for the sake of time, let me just go ahead and locate that. It's going to be E. So let me just tell you why it's E. And if you want, you can look at the other four choices here. But remember, we said if you have a strong acid and a strong base, it's going to give you a neutral salt or a neutral solution. So what we're looking for here is what? If we want a basic salt or solution, we need a strong base and a weak acid. And it turns out that E provides that because the SO4 here came from HSO4, not H2SO4, because that would have produced HSO4. So this came originally from HSO4 minus, which is a weak acid. And then, of course, the Na came from NaOH, which is a strong base here. So strong base, weak acid, basic salt, or basic solution. So the answer is going to be E. And let's go ahead and move on because we have some really strenuous problems still ahead. So next. This one, number 8 here at the top, of the following, which is going to be the strongest acid, you're looking for the one that has the most either oxygens, but they all have the same number of oxygens. So next, look for this one that has the most halogens or halogens. So that one that I underlined has 3. This one doesn't have any. This one has 1. It's not the same one, but it's still. And then this one has 1, and this one has 2. So your answer is going to be the one that has 3, which is A. And then for number 9, the strongest acid produces the weakest base. So if we're looking for the one that's going to produce the strongest base, we want the one that was originally the weakest acid. And we can tell that by looking at the K number. We want the lowest K number, which is that one. So it's HClO. So the conjugate base of that will be the strongest base, which would be, what would the conjugate base of HClO be? It would be the HClO if you took the H off, which would be what? Which would be ClO minus, which is answer choice B. And that's another thing that I should point out to you guys now, is that you'll notice that they didn't keep the same order that they had in that table when they listed these down here below. So you have to be really careful about that. You want ClO minus, so you want that choice right there, not the third choice, which would have been wrong. Next slide. We're going to be getting into now some more problems like the ones we had before. So calculate the percent dissociation of acid in each of the following. 0.5 acetic. So we're going to do this the same way. We're going to have 0.5 up at the top left, and we'll have 0 plus x is x on the right. We're going to assume that x is negligible. That 0.5 is kind of small, but the K value is 1.8 times 10 to the minus fifth. And that isn't actually given to you here, but for acetic acid, I mean, it would have to be given to you really, but you'll probably remember it after you've done it enough, right? It's 1.8 times 10 to the minus fifth, and that's for acetic acid, and we use it all the time. So you might just want to memorize it. And that way, if it is left off like on a test accidentally, you'll know it and you won't have to wait until I write it on the board or until I email you and give you the right value. Not that I'm anticipating that happening anyway. So let's go to the next slide and look at how we set this up. So we just did this the same way. We assumed that the x was small here. That's a little concerning, but it turns out that it's actually okay in this case. Even though that initial concentration is low, the K value is very low. So it works out okay because it turns out that the error, which will be the same as the percent dissociation, is only 0.6. It's less than 1%, so we're good to go here. Everything else here is done exactly the same way as what we've done in the past. So why don't we go ahead and move on, and I'll let you pause here if you want and look at this in more detail. So next slide. All right, so now this is something we have not done. A 0.15 molar solution of a weak acid is 3% dissociated. Calculate Ka. The way that you have to do this is kind of a trick. So for this problem and also for the next one, you'll want to write these down if you don't already understand them. There's a trick to these. So you'll want to be sure that when you take the exams that you understand the ones that have to have tricks. Whether it's in this chapter or any other chapter, there are certain problems that you just have to remember. This problem has to be done a certain way. So the way that you have to do this is you have to convert that 3% to a decimal. So that's going to be 0.03. And multiply that times 0.15, which is your initial concentration. And that's going to give you your x. And that's the only way that you can do the problem. So if you can't remember this, you're in big trouble for this problem. And the reason that I just drew that line that went up to the top left is because I was pausing the video and I didn't let up quite fast enough on this marker. So just ignore that. I think I did that earlier too, either in these or in the lecture notes. So whatever you get here, anyway, when you multiply 0.03, and the 0.03 is what I got when I changed the percent to a fraction or a decimal. Just move that decimal back over 2 places to the left, which is equivalent to dividing it by 100. So whatever you get here is going to be your x. And it's going to be something with a 4 or 5 in it, but I'm not sure where the decimal is going to be. So it looks like it's going to be like, well, I'm not even going to hazard a guess here. So whatever you get is going to be your x. And we're supposed to find the Ka. So whatever we get for the x, we'll then use that for the x, like at the bottom right in the 2 columns, right? We usually have 2 of them. So we have to multiply x times x, and then we divide that by 0.15 minus x. So whatever you get here for x, you'll also want to remember to come over here and subtract it from the 0.15 to get your equilibrium concentration for your weak acid. And we don't know what this acid is, but it doesn't matter because we can still find the Ka. So once you get that value there, which I'll underline, then we take x times x divided by that, and that's going to be the Ka. Next. So here it is. So when you multiplied the 0.15 times the 0.03, you get 0.0045. I couldn't remember how many zeros were in there, which means that this is going to be 0.0045, and so is this. And also, you're going to have to subtract 0.0045 here from the 0.15 to get your equilibrium concentration for your HA. Now remember, it's the equilibria positions here that we care about. That's what we need, what these concentrations are on this bottom row. So now you have a number for this, you have a number for this, and you have a number for this. So just go ahead and do your x squared over 0.1455, and that's going to give you your Ka, and you're finished. So for the sake of time, let's go ahead and go on to the next one. And this one also has a trick. So I'm put a little asterisk or star up here. So you'll have to remember this, and we did talk about it also in the lecture notes. When they give you the pH, the way that you get the x is you do it the same way we did to get the H plus concentration, right? You raise 10 to the power of the pH and put a negative sign in front of it. So in this case, you raise 10 to the minus 2.7. We said that was called taking the antilog, and that's going to give you the concentration of H3O+. But in this kind of a problem, it will just basically, it'll give you your x. So that is going to be x. So just do that on your calculator, and whatever the number is that it spits out is going to be x, which is going to end up at the bottom right of your chart or your table. And then to get the initial concentration, what you can do is you can say Ka equals x squared over, let's see now, how would that work? Let's actually, let me think about this for a second. Yeah, so you know what x is, right? It's 10 to the minus 2.7. Whatever you get when you do this is going to be your x. So you know what that is, and you know what Ka is. And you know that Ka is going to be this number that you got for x squared divided by some other number, which we could call y. So when you get the other number, you're going to be getting the equilibrium concentration of your formic acid. But that isn't what they want. They want the initial concentration of the formic acid. So add back to that whatever you got for your x, and that will give you the initial concentration. So let's go ahead and look at that on the next slide. So we figure it out by raising 10 to the minus, so let me just circle it. 10 to the minus 2.7 is 2 times 10 to the minus third. That equals x. So Ka is going to be x times x over this. So Ka we know because they gave it to us up here. And also we know what x is. So we can solve for that thing right there that I'm circling right now. And when we do that, let's see if I can figure out where that is. We get 0.022. Now you'll want to do this yourself. First of all, go back and make sure that when you do 10 to the minus 2.7, you get that. And then go ahead and see if you can solve for this thing right here, which you can call y if you want to. And you should get 0.022. But they didn't ask for that. They asked for this right here. So you have to add the x here that you got in the first step to what you get for this step to get that, which is what they want. So in other words, you want to add the 0.022 plus 0.002, which is what you got here for x, which I did right here. So 0.022 plus 0.002 is 0.024 molar. And that is our answer. Okay, so be sure that you remember or mark these last two because they have a trick to them. Okay, let's go to the next slide. All right, write the reaction and corresponding Kb expression. So we're going to have for A, NH3 plus H2O gives NH4 plus OH minus. For B, we're going to have C5H5N plus H2O gives C5H5NH plus OH minus. And then the equilibrium expressions will be Kb for A would be, let's see, NH4 plus times OH minus over NH3. And for B, it would be that Kb equals C5H5NH times OH minus over C5H5N, where all of those are concentrations. So let's go to the next slide and look at the answers here. And here are the things that I just said. So pause this here if you want and look at this. These are just Kb expressions. So whenever you have either Ka or Kb, and I hope I'm not boring you by saying this over and over again, you have to be adding these things to water. And again, just as I've said several times previously, if you have anything other than water being added, then you're not doing Ka or Kb. So anyway, let's go on. Calculate the pH of the following solutions. So 0.1, let's just do A first. That means it's 10 to the minus 1, so you might want to get used to thinking of them that way. It's the same thing to say 10 to the minus 1 as it is to say 0.1. And so, but if you write it this way, it's easy to see the exponent. It's minus 1, so if you take minus a minus 1, you get a plus 1. So that means that the POH, because this is the concentration of the OH here, so this is NaOH, it's a strong base, so if you put it in water, it completely breaks up. So the POH is 1. So what's the pH? Well, 14 minus 1, right, which is 13. But you'd have to write it as 13.00 because you have to have 2 decimals because of the 2 sig figs here. Here, this is the same trick they pulled before with the acids. That concentration of NaOH is lower than the OH minus concentration that's already present in the water. what is the concentration that's already present? 10 to the minus 7th, which means the pH is going to be 7, the pOH is going to be 7, so the pH would be 7 for part B. And then C is an example of when you have more than 1 molar strong base or acid. In this case, it's a base. That means the pH that you get for part C is going to be larger than 14. Now, I know that a lot of times in like biology text, they'll tell you that pH goes from 0 to 14, but that's actually not true. It can go to negative numbers for strong acids. And in this case, we're going to get a plus 14, and I actually think it's, from memory, I think it's actually 14.3. Because this is a strong base, and because the concentration of that strong base is more than 1 molar. And you say, well, you probably don't deal with those. Yeah, they do. I mean, in the laboratory, they do typically tend to dilute the acids that we use in the lab. And most of the time, we'll be using like 0.1 molar. And that's so that if we spill it, we don't burn the heck out of ourselves. But when they get it into the stockroom, it sometimes comes in like, I don't know for sure, but I think I'm sure that I've seen it at least 6 molar. And so for both the acids and the bases, and it may even be higher than that. All right, so anyway, and then we'll want to have how many decimals too. So, I mean, technically, I won't count off for this, but it should be written that way. Let's go to the answers, and then let's go ahead and move on. What are the major species present? Now, this is a weak base problem, so let's do this a little more slowly here. So we're going to have a weak base. We want Kb. That means we need to write, I mean, I'll try to write this out. You won't be able to read it anyway, probably, but NH3 plus what? So think about what we're going to add. What's the other thing that's available? I mean, if nothing else, sometimes that's the way you can remember. The only other thing that's around is just H2O. So if we add H2O to NH3, what will happen? And remember that you're going to have to supply these equations on your own. So I'm doing them for you now, but you'll have to figure out how I'm doing them. So what would happen if I reacted NH3 with H2O? Well, one of the H pluses will come off of the H2O and make that into what? NH4 plus, or ammonium. And what will that do to the water? What will that become? This is just unbearably slow. Okay, anyway. What will the water become? Whoops. Plus what? OH minus, right? So if you take an H plus off of the water, you get OH minus. Okay, it's just so hard to write with this bloody thing. Just drives me up the walls. So that's going to be written across the top of our ice table. This is going to be our Kb expression. Kb will be this times this divided by this. And here underneath NH3, we're going to have 0.15. And what are we going to have under NH4 plus? Zero, right? And what about OH minus? 0. And is this 1 to 1 to 1 here? Yes. So I'm not going to write it, but it's going to be minus X here, and then plus X over here for these two on the right. So at the bottom, we're going to have X and X. So you can see these work just like the acid problems, but you just have to be careful and realize what's happening here. This is going to be 0.15 minus X. All right, so let's see. Calculate the OH minus concentration, which is when we get the X, that's what we'll have, right? Because that's what one of the things that the X represents there. Also, when we get the X, if it represents the OH minus concentration, then if we take minus the log of that, we're going to have ourselves a pOH. But then we have to subtract that from 14 to get the pH. We can answer the first question here right now. The major species are going to be NH3, NH2O, and then let's see what else. Okay, I see what we're missing here. So we're missing. So why don't you see if you can think of what is it that we don't have here that we need. What else do we need to find X here? We need KB, right? And it's not there. So it turns out, and so if you get a situation like this, you'd have to let me know, hey, you didn't give us the KB. Hopefully that won't happen. But the KB, you may remember that we said this before, is the same number as the Ka for acetic acid, and it's 1. I'm not going to write it out, but it's 1.8 E minus 5. So that would equal X squared divided by 0.15. So 1.8 times 10 to the minus 5th will equal X squared divided by 0.15. So solve for X, let's slide. And you get that it is 1.64 times 10 to the minus 3rd. So that's going to go here and here. And then if you want, you can subtract it from this and get the equilibrium concentration here for the NH3. And we don't need to do that because they didn't ask us to do the concentration of all species. So what did they ask us to find? The pH. Okay, so whatever you get for your X, which is 1.64 times 10 to the minus 3rd, take minus the log of that, and that will give you the pOH. Again, so be careful. That's not the pH, it's the pOH. To get to pH, you subtract it from 14, which is done here, and you get 11.220, and you have 3 decimals because you've got 3 sig figs up here. And let's go ahead and move on now to the next problem. All right, calculate the pH of 2 molar H2SO4. The trick here is that you don't want to assume that you're losing 2 protons there, because this is a polyprotic acid, so you only have to worry about the first one. So if you have 2 molar H2SO4, it's a strong acid. You do it the same way you would do it if it were HNO3 or HCl. You just assume that it's going to completely dissociate, and your H plus concentration will be a 2.0 also. Now it's more than 1, so that means we're going to get a negative number for our pH, right? So if you do this on your calculator, you just take minus the log of 2, which, if I'm remembering correctly, you're going to get minus 0.3. And it would have to be minus 0.30 because of the 2 sig figs in your concentration. So let's go to the next slide and see if it's right. Yeah. So this is actually a negative number here because this concentration is more than 1. So don't do this like multiply this by 2. Now we did that earlier with, I think it was calcium hydroxide, but that's because hydroxides and bases are different. They act differently. So in a case like where you have calcium hydroxide, it will break up into 1 calcium and 2 hydroxides. But acids that are polyprotic acids don't work that way. They just break up. What will happen will be that all of the H2SO4s will break up into H plus plus HSO4 minus. And then you won't start to get the second proton coming off basically until all or almost all of the H pluses have come off of the H2SO4. So remember we said that when you're doing pH problems, if it's a polyprotic acid, that you just don't worry about anything other than just the first proton. So let's go on now to the next slide. Arrange the following concentrations, 0.1 concentration solutions in order most acidic to most basic. They all have the same concentrations. We don't have to worry about that. So most acidic, well, that's going to probably be this one, right? Most basic, well, they've got them right in the right order so far. And then the KCl would be in the middle. And then this one is going to be basic, so it would be between these two. And this one's going to be acidic, so it's going to be like right where it is. Now, this is going to be a weak acid. This is going to be a weak base. So it would be HCl, and then this, and then KCl, which is neutral, and then the weak base, and then the strong base. Next slide, and then let's go on to the next one after that. For these, we're supposed to put them in increasing acid strength. So this one here is going to be more acidic or stronger acid than that one because bromine is more electronegative than iodine because it's further up in the chart. And for part C, it's the same thing. The HOCl will be more acidic than the HOI because it's further up which means the Cl is more electronegative. So remember that we said something about that was one of the factors, but that it wasn't the most important factor, and that was the polarity of the bond. So the more electronegative these things are, the more polar the bond will be. But that's not the only thing you look at, but in this case, it's determinative. It will decide the answer for you. For B and D, we're looking at the number of O's, and we've got more O's on the right than we do on the left, other things being equal. And for part D, we have more O's on the left than we do on the right. So the ones that I just underlined will be the stronger. Let's go to the next slide and the next. The Lewis acid and Lewis base, whenever you've got boron, as I said before, remember an acid is a proton donor or a electron acceptor, so B will always be the answer for your Lewis acid. So here that's going to be the Lewis acid. So for A and C it's easy, right? It's just the thing that has the B in it is going to be your Lewis acid. For C, this is going to be the Lewis base because it's got 4 lone pairs that it can donate to that poor boron. And then here the O on the H2O has 2 lone pairs, right? Which they can, either one of those can be donated to the boron. So the boron only has 6 electrons around it typically, so it's always on the lookout for more electrons. For part B, it's very similar. Ag plus also will be electron deficient, so it will be looking for electrons, so it's going to act as the Lewis acid. And the lone pair here on the NH3, or I mean if you want to just consider it to be the NH3, will be the Lewis base in that case. Next, and then I'll go on to the next one. And then here is this problem that I've typically given in the past, not recently, for bonus question, because they want you to find the PO4 3- concentration. To do that, you have to start with your H3PO4 at 1 molar and use this Ka value and get the concentration of the H2PO4-, and then do it all over again, another ice table, and get the concentration of the HPO4-2-, and then do it again to get the concentration of the PO4-3-. So let's just kind of look this over. I kind of doubt that I'm going to ask this, but just in case, you might want to just look it over. But if I do ask it, it'll just be for a bonus. It won't be part of the regular test. So let's go to the next slide. So here's the first step. You're starting off with 1. And remember that if you're going to do the pH, this is the only step you have to do. And then this problem is actually made worse by the fact that you have to use the quadratic equation here. So you have to solve for x, and we did this before in the lecture notes. We found that x was 0.0829, so this may be familiar to you. Excuse me. So you would subtract this from your original concentration of 1 for your H3PO4, and that would give you its concentration at equilibrium, and then your x here will be your concentration that you would use for the second step for that. So this is the way you would have to start off the second step. So you would transfer this over to a new ice table, and it's going to be 0.0829. Next, so you start here with 0.0829, you do it all over again, use the Ka2 expression this time, you use a different constant, and when you do it this time, you get to the x, and you can see how much it's dropped. It's now down to 6.2 e minus 8, and then you would have to subtract that from 0.0829 here to get whatever your equilibrium concentration is. And then also to get the HPO4 here, you just use your x, which is this ridiculously small number, 6.2 e minus 8. So let's go to the next slide. So you put that here. And it's already an incredibly small number. And then you do it all over again, and you wind up with x here is 3.6 times 10 to the minus 19th molar, and that is your answer. That's what you got for your x here. So you just do the same thing 3 times, which is why I've kind of stopped asking this. So anyway, let's go on. I think that's it. Yeah, so let's go ahead and wrap this up. It's right at 1 hour. And that is the end of chapter 16, so I'll see you in chapter 17a.